So now I would like to share my experience on using this radar training kit. So the radar training kit typically it will consist of several modules, and through this radar training kit we actually can learn. We can expect the learning outcomes from this radar training kit, such as through this experiment we are expected the student are able to learn what is about radar operation. Okay, they should understand how the radar operate. We also, since this radar training kit is also equipped with various waveform that can be generated in baseband, so we are able to explain the different radar configuration, and also via the signal that captured. We are able to analyze the radar system, okay, for to convert the information that we extract to the related information, such as the range, the Doppler shift, the speed, etc., via some processing, right? Okay, so of course, via the experiment, most likely we will use some measurement tools such as oscilloscope, spectrum analyzer. Then you will let the student have some exposure for the high-end RF measurement technique, right? So in this radar training kit, basically is equipped with the transceiver module, right? So the transceiver module will have the transmitter and receiver on board. The antenna, okay, one will be act as the transmitting. The other one will be act as a receiving antenna. Okay, there is a synthesizer software for us to choose what is the signal that we want to generate, right? So this is very useful so that the student will experience different kind of radar waveform, right? Is to be transmit, and what is the behavior of the outcome when we use different type of the waveform, right? And of course, there is some accessory for us to do different types of experiment, okay? So as Mr. Lim have mentioned, there are several of basically 2, 3, 4, 5, 6, 7, 8, 9. Basically, there are 9 experiments, right? So 6 of them will be using the radar training kit to conduct, okay, for hands-on session, right? So the rest will be on the simulation. So I will talk more about on the hands-on session, what we can expect the student learn, okay, via this experiment. Okay, so I only pick a few experiments they are interested, all right? Because some of them are actually to let the student more familiar with the system. So I only pick those that are pretty interested and related to directly to the information that we want to extract. Right? Okay. So one of the experiment is the RF spectrum measurement and analysis. Right? Okay. So the whole setup is we have a radar system setup, right? Okay. And we have a target, right? In this case, is a flat metallic plate, right? So this flat metallic plate will act as a target, and the student have to measure the distance between the radar training kit, okay, and the target, right? And measure the receive power via the spectrum analyzer, right? Okay. And subsequently, the student will change the distance, okay, to different distance. Okay, example from here, we can see the student need to place the metallic plate at different position from 10 centimeter to 100 centimeter, and the student have to record down what is the receive power via the spectrum analyzer, right? So via this experiment, then the student will be able to relate the distance and also the power that we receive, right? So through the theory or through the class, right? So we will teach the student about what is the radar equation. So this is the radar equation. So the radar equation will relate to some of the parameters such as the power, transmitted power, the gain of the antenna, the wavelength, the target characteristic, the distance, and the losses in the system. All right. Okay. So through this measurement, okay, it is very useful that to relate the received power to the distance of the target, right? So the student via this measurement result, okay, can verify the relationship between the received power and also the distance of measurement, all right? So they can verify whether this relationship is correct and to further strengthen the study of this Friis equation or radar equation. Okay, so this is one of the very useful experiment so that the student will have the experience of the measuring the received power via different distance. All right. Another very interesting experiment is the Doppler measurement, right? Okay, so Doppler measurement means we are measuring the frequency shift due to the movement, right? So when there is a relative movement between the radar and the target, right? Okay, so the relative movement means it can be a target moving or it can be the radar is moving, right? So of course, in this case, the target is moving, radar doesn't move. So when there is a target is moving, right? So this target, the return signal will actually will be embedded with the frequency shift due to the Doppler effect, right? So when the target is moving, there will be a Doppler shift, and this Doppler shift can be measured by the radar system, right? Okay, so over here we have 3 examples, right? So if the target is static, right? If the target is static, okay, we can measure the return signal, right? We can measure the return signal and we view in the time domain, right? Via oscilloscope, right? So when the target is static, means there is no movement, right? There is no movement. The Doppler shift will be 0, right? So the return will be static, right? So the return will be static, means there is no movement on the time domain receiving signal. Okay. So when the target is moving, right? Okay, we can look at the relationship between the movement and also the Doppler frequency, right? So the V is the velocity of the target, the FD is the Doppler frequency, the lambda is the wavelength, right? So when there is a V, when there is a velocity, when there's a target moving, we actually will produce a Doppler frequency, right? If the V is 0, so Doppler shift is 0. If V is certain value, then we have a certain value of Doppler shift because the F typically is fixed. All right. So over here, the second graph, right, is actually showing the moving target of a human being, okay, walking in front of the radar system, right? So we observe, okay, there is some swinging of the signal, all right, because the most likely the human being will not walk in very steady velocity. So the frequency may be vary, right? The amplitude also may be vary, depends on the distance, right? So if we use a small fan, okay, placed in front of this radar training kit, right? Since the fan typically will rotate in the constant speed, okay, therefore the return of the Doppler frequency will be steady also. Okay, example, right? So you will see there is a small sine wave. If we are able to measure the Doppler frequency, then we are able to calculate what is the velocity of the target, right? So this is a very interesting experiment because the student can directly observe the moving of the time domain signal, right? When there is a target moving in front of the radar system. Okay. So another experience will be on the different signal, which is FMCW radar, right? So in this case, we will use the delay line to simulate a single point target, right? Okay. So why we are not using, I think if we are using an antenna to measure the surrounding area, so in the lab, most likely the reflectivity, the reflection from the lab surrounding is very noisy. So it's not easy to see the target. So using a delay line will be a good choice to simulate a single point target, right? So the signal will transmit via the transmitting antenna, right? And will delay. Okay, so the delayed signal is based on the length of this delay line, right? So the signal will be delayed, the RF signal will be delayed and received by the receiving antenna. Okay, so this will simulate a single point target with a particular distance. Okay, so the signal received will again view by the oscilloscope. Right? Okay. So since it's a single point target, so we will expect a single frequency signal to be appeared in the oscilloscope. Right? Okay, so the frequency of this signal can be captured, can be measured, right? So the relationship between the distance, the bandwidth, the delay, and also the frequency measured are shown in this equation, right? So the FIF is actually the frequency that we captured when it is now converted to the by receiver. So this FIF is actually this frequency, right? So the frequency measured by the oscilloscope is FIF. The B is the bandwidth of the FMCW radar. The R is the distance of the target. C is the speed of light. The T is the cycle of the FMCW. Okay. So using this equation, then we are able to calculate what is the distance. If we are able to measure the down converting frequency. Okay, so the FIF is measured from the oscilloscope, right? So if you plug in into this equation, we actually can calculate what is the R, the distance. So once we calculate what is the distance, then you can calculate what is the delay, and you can cross-check with the delay line specification. Okay, so this experiment, the student will be able to experience how the FMCW radar signal works. All right. Okay. So again, this is a very good experience because this is very different from the CW radar, right? So the CW radar is only able to measure the Doppler frequency, but not able to measure the range. But the FMCW can measure both the range and also the frequency shifted due to Doppler frequency, right? So another type of signal that can be generated by this radar training kit is the linear FM pulse. Right? So it is a pulse radar, but within the signal itself is the linear FM signal, right? Okay. So the linear FM signal is actually, you can see over here, right? Okay. So this is a linear FM signal. Okay. So the frequency will change according to time. It's a linearly shifted, right? It's in a pulse form, right? It's in a pulse form. So when this signal is transmitted, okay, from the transmitting antenna, okay, and it will be delayed by the delay line and received by the receiving signal, right? Okay. So if we display both the transmitting and the receiving signal at the same oscilloscope, right? So the orange one represents the transmitting signal, right? So the green color one represents the receiving signal. All right. Since the signal actually passed through the delay line, so we will expect there is some delay. Okay. So this delay is actually due to the distance travel. Right? So this delay is due to the distance travel, the RF frequency signal travel in the delay line and received by the signal. Right? So if we zoom in, right? If we zoom in this received signal, right? So you can actually observe the transmitting signal, okay, the beginning edge of the transmitting signal, and the beginning edge of the receiving signal, actually they have a certain gap. So this gap is called the delay time, right? So the delay time will be directly proportional to the distance that the waves propagate. Okay, so so it means that via measuring of this delay time, okay, we actually can reverse calculate what is the distance being traveled by the signal. All right. So this is the principle of the pulse radar, right? So how the pulse radar can extract the range information is actually via the um, calculation or measure of the delay time between the transmitted signal and the receiving signal, right? So once we are able to measure this delay, okay, then we are able to reverse calculate the range that the system travel, right? So this will let the student understand how the pulse radar is operate, right? Okay. So another very important experiment is the radar cross-section measurement, right? So if you observe the radar equation, right? If you observe the radar equation, so the radar equation will consist of various parameters. The received power is equals to the transmit power, multiply with the gain square, lambda square, and the sigma, all right? Okay, so this sigma is the property of the target, right? So this sigma is the property of target divided by 4 pi cube r power of 4. This is the distance. L is the radar system loss, right? Okay. So the parameter that concern with the target is actually the sigma, all right? So this sigma actually is describe the behavior of the target, okay, in terms of their size, in terms of their shape. Okay, different shape will have different reflectivity. In terms of the angle of viewing, depends on their moisture content, depends on the material, etc., etc. Okay, so all lump into this sigma. All right. So if we are able to measure the radar cross section correctly, meaning we actually can perform more high-end analysis, okay, such as classification. Example, when I measured paddy field, right? When I measure paddy field, the sigma will be in certain value, okay? When I measure, say, rambutan tree, right? So the rambutan tree will have different reflectivity, means different sigma, right? So if we can extract the sigma correctly, means we actually can do a classification, right? So this is how the importance of this radar cross-section measurement, right? So in this radar training kit, so there is experiment also to measure the signal in order for us to calculate the radar cross-section, right? So we place a target in front of this radar training kit, and we measure the return signal via the spectral analyzer, right? So spectral analyzer is able to measure the return power, okay, via viewing of the spectrum of the receiving signal. As all the other parameter we can obtain from the radar training kit. Therefore, if we plug in all this receiving power, transmitting power, the gain of the antenna, the frequency we are using, the distance, and also the estimation of the system cost, then we are able to calculate the signal. All right. Okay. So there is two different type of target used in this experiment. One is a flat metallic plate. The other one is a trihedral corner reflector. Okay, the spelling from trihedral corner reflector. Right. So we can measure the different power received by these two targets, and then we can use this equation to calculate what is the sigma. And of course, we also can use the theoretical equation to calculate what is the sigma or the radar cross-section of the target. Okay, there is a standard equation for us to calculate that. Same go to the dihedral. Then we can compare what is the actual radar cross-section measurement sigma and also the theoretical, and we can compare the result respectively, right? So this is a very useful experiment because it spell out the different characteristic of the target will have different reflectivity. All right. Okay. So the student will experience when they replace with different target, right? All right. So in conclusion, that we through this experiment, we actually can learn different type of the radar operation, right? Okay, so we can perform the radar Doppler measurement via the continuous wave radar system. We can measure the distance, okay, via the FMCW radar system. We also can measure the distance via the linear chirp pulse radar. We can verify the radar equation, okay, via the distance by varying the distance between the radar and also the target. We also can measure the radar cross-section, right? Okay. The student will also experience different type of the baseband signal being generated. Okay, so the baseband signal is generated by the FPGA board embed into the radar training kit, right? So by choosing the correct baseband signal, then the student will have different experience on what they are actually transmitting, right? Okay. And of course, Mr. Lim also mentioned about the user can actually self-define, but that will involve some programming onto the FPGA board, right? So that's all my sharing. Thank you very much.